We are running a modern large language model at 20 tokens per second on a 15-year-old Dell server. Specifically, the system is a Dell T7400 powered by dual Xeon X5472 Harper-Town processors from 2007. If you install standard LLM software on this hardware, it fails. The CPU generates a completely unusable 0.05 tokens per second. But the server's RAM can push data to the processor at 6.5 gigabytes per second. This horizontal bar chart compares that 6.5 gigabyte capacity against the fractional output actually being processed at 0.05 tokens per second. If a compressed 2.8 gigabyte model moves at the system's maximum bandwidth, the hardware should theoretically generate a token in under half a second. The hardware is stalling because of what the processor is forced to do with the data once it arrives, not the transit time. Inside the CPU, the standard inference pipeline relies on the arithmetic logic unit, or ALU. Quantized, integer-based neural network weights arrive from memory and enter the processor. This flowchart illustrates the choke point, a bottleneck labeled float32 conversion. The rapid stream of integers slams into this mandatory step, staggering the flow as they are unpacked back into decimals. This conversion imposes a hard ceiling on the older SSE 4.1 architecture, limiting the processor to 4 gigaflops. The CPU exhausts almost all of its available clock cycles expanding data structures, rather than performing actual math. The multiply-accumulate operations, the mathematical foundation of neural network inference, are completely starved of resources. To reach the true speed limit of this silicon, floating-point math and the ALU must be bypassed entirely. The bypass relies on computing without traditional arithmetic, mapping complex mathematical operations instead directly onto physical state machines. This is the Basin Quotient Machine, or BQM, a discrete logic engine discovered inside a simulated ring of coupled oscillators. Instead of numerical floating-point values, states in this system are defined by topological winding numbers, identified by the integer q. This graphic shows the n-ary encoding structure. Topology creates stacked energy-layered attractors representing varying stability. In a 16-site ring, exactly 7 stable states exist within these deep gravity wells. These 7 layers map precisely onto a low-radix logic structure, forming an efficient discrete encoding system. Because these topological states are strictly bounded, calculating the transitions between them requires zero math. To run an LLM on this structure, the network must be compressed through teacher-student distillation. The original teacher model contains 14 billion parameters. The distillation process extracts that knowledge into a 500 million parameter student model restricted entirely to ternary weights, values of -1, 0, and +1. This animation shows a standard matrix multiplication equation dissolving and restructuring into a static grid array. The BQM logic allows every possible calculation in the ternary student model to be pre-computed. Dynamic arithmetic is replaced entirely by an O1 array lookup. A complete 4-state transition table requires exactly 16 bytes of data. By compressing inference rules into 16 bytes, the entire operational logic of the model lives permanently inside the CPU's fastest, most localized L1 cache. Those 16 bytes have a precise hardware destination, the 128-bit XMM CPU register. This 128-bit register drops into frame, perfectly matching the 16-byte transition table. This alignment exploits a silicon instruction called pshufb. Instead of computing math, it shuffles bytes. By feeding quantized weights as indices, the hardware maps 16 parallel outputs instantaneously, bypassing the ALU. This exploit drops the execution cost to 1.1 CPU cycles per multiply-accumulate operation. A single legacy core suddenly achieves a raw throughput of 2.8 gigamax per second. By treating neural network weights purely as topological indices, this method effectively tricks the older CPU's shuffle unit into performing massive parallel computation. Applying this logic to a full transformer requires splitting the inference pipeline. This architectural schematic of the BQSM engine shows incoming data splitting into 2 distinct paths, an int8 attention block and a BQSM SIMD FFN block. The attention projections have a small dimensional footprint, allowing them to remain in standard 8-bit integer formats without stalling the system. The dimensionally massive feed-forward network layers are routed exclusively through the pshufb transition tables. This hybrid routing preserves mathematical precision exactly where it's required, while accelerating the heaviest compute burdens topologically. The result is a leap from 0.05 to roughly 20 tokens per second on a 15-year-old machine. Neural network layers no longer operate as math equations. They execute as physical state machines. The cost of an operation is determined by coupling efficiency and physical energy barriers, rather than raw flops. This topological execution completely sidesteps the brute force arithmetic architecture of modern GPUs. Topological computation proves that legacy silicon can be exploited to run advanced AI by changing the physical definition of the operation itself.